test will be in class on the Thursday, 2 weeks from now. Okay? So it will be from 9:30 to 10:15, right here. I'll be out of the country on that day, so I'm going to not be here. And I will have more detail regarding test 2 as we get closer. But there's no change needed. You're supposed to be here anyway. So I just want to let you know well in advance so you can participate. All right? So I am collecting the midterm. Please make sure you put your name down because you will get credit. And just pass it up front. And I will collect them, I will read them, and return that back to you after you have entered a grade in your homework. So for the assignment, we are starting chapter 8 for the reading on internal pipe flow today. And I'm just again asking you to review your notes on 21, 24 regarding the pipe flow. This is the second time or third time I asked you to do that. So I just want to put everything together in a bigger perspective in reference to what you learned prior. Homework is 2.5 hours. I will touch on each one of them, so that it should be pretty clear. Another set of homework we'll talk about that later in the week. So today we're going to finish up dimensional analysis. And what I'd like to do is to look at modeling testing, which another word for that is similitude. And I'm going to look back at the 2 homework due today. All right. Please upload your homework also for today, despite the midterm evaluation. So Mike will grade your homework, and I will look at your midterm evaluation and count it as 2 homeworks, 1 each. All right. And using those 2 examples of your homework, I will tell you some of the pitfall or drawback of wind tunnel testing, both at National Lab like NASA, as well as near the Randolph wind tunnel here at Virginia Tech. And then I will touch on the new homework, which also has to do with similitude or model testing. And the half of the lecture will be devoted to pipe flow, mainly on the use of energy equation. So finally, we're actually going back to chapter 5 and look at how energy equation can be used in addition to continuity, continuity, and momentum. So that's one of the final key equation that will be in our toolbox. So today we're going to look at the application of energy equation by an example. And then subsequent nature, maybe next week, I will show you how the equation come about. So application first, derivation later. Any question before I start? That's the roadmap for today. Any question on the end of the assignment? Again, if you came in late, please pass your homework up front for the midterm evaluation. So problem 764 is typically for people who work in the automobile industry, Ford, GM. They all have their own wind tunnel, of which they test sometimes a full-size automobile. But there are times they test a model. So the problem stated that you have a prototype. Full-size car, 20 feet in length. We're going to test a much smaller model, 4 foot. Say at the Virginia Tech wind tunnel, which is barely big enough. That wind tunnel is about 6 foot in cross section, so it's barely enough to fit this model in there. What have you learned from this homework? The question asks you, can you feasibly match the Reynolds number? What's your take on that? You've done the homework, right? So to match an automobile at full size at 60 miles per hour, what is the speed in the wind tunnel for a smaller model by 1/5? How fast I have to run the wind tunnel airspeed in order to match Reynolds number? the answer is 450. So what's the big deal? Want the fan faster and drive the airspeed faster? Yes?
Is it 450 for 60 miles per hour or for 90?
Did I say, for 90, I'm sorry, right, 90, thank you. Yep, I misread it. For 90, yes, thank you. But, same question. I just want to tunnel at 450 miles per hour. Anyone? Yeah,
You have to maintain density as well.
you have maintained density. Density maintained is atmospheric pressure tunnel, meaning there's no pressurized, so density is still ambient, right? Pressure, temperature won't change at our wind tunnel here on campus. So what's the catch?
It's too fast.
It's too fast. How fast is the airplane flying? I've mentioned that several times. That's 30,000 feet. In miles per hour or in Mach number? Mach number is about 0.8. I mean, typical airplane speed is like 250, 275 miles per hour. You're flying almost twice the speed of that. You're going supersonic, right? Which is very difficult to achieve, number one. Number two, if you do, the air is going so fast, you are no longer considered incompressible flow. At 400 miles per hour, there's shock wave, which is not what you see at 90 miles per hour. So you're not quite matching another dimensionless perimeter, which we didn't touch. That's called the Mach number. So the takeaway is, it seems very simple and easy to claim this matching in real life is not typical. So that's example one. Example two is actually the airplane, which is at 30,000 feet, 240 miles per hour, and at 10,000 feet, I'm going to do a scale model testing, 1/20th the size, which is again a size small enough that we can fit in our Virginia Tech wind tunnel with 6 foot by 6 foot cross section. So the difference at 10,000 feet is you have to account for what? What's the difference between that and sea level static at takeoff? Or 30,000 feet cruise altitude. This is cruise altitude for a small commuter plane, like going from here to Charlotte. From here to San Francisco, or from DC to San Francisco, on the 787, you'll be more like 35,000 feet. So what's the difference between sea level and 30,000 feet? Density and what else? Viscosity, right? That's the Reynolds number perimeters. And it comes about because of the change in altitude. Both pressure and temperature changes. And they are now being captured in our viscosity, which is a function of temperature, and density to account for the pressure and temperature change. And when you work out those numbers, here's the takeaway. To match the Reynolds number in the model test, you have to define that fast. And if you have a problem doing at 450 miles per hour, this is of course nonsense, right? This is the speed of a bullet. No easy wind tunnel you can build to hold the air at that speed. So what's the bottom line? What have you learned from this homework? Anyone? So what's the difference between these two homework versus the example we did in class, which is that airship, that blimp?
The fluid.
The fluid? No, I don't think that is what I want to hear. And you have another homework which you have a balloon. It's a balloon. What is the characteristic of those two problems? Yes?
They're moving slower.
They are moving very slow, a couple of feet per second. They're what you literally call creeping flow. Creeping flow meaning creepy, just barely moving. Only under those circumstances, which is not practical for a lot of engineering application, right? Only for those applications, you can hope to match the Reynolds number, as well as other dimensionless perimeter like Mach number. And they're fine in between, more practical problem, automobile, airplane, ships, you name it, they are not readily available for perfect similitude. So, we play trick. We cheat. How? So typical NASA wind tunnel, which is bigger than Virginia Tech, we put an airplane here, and you make measurement. The diameter of that maybe 10 feet, twice the size of what we use. The perimeter you want to match, like we mentioned many times, first and foremost is the Reynolds number. In addition, you also want to match, which we didn't cover, so-called Mach number, which is the velocity of the vehicle divided by c. Anyone want to guess what c is? Speed of sound, which is typically in meters per second, how much? 330, right? So Mach 1.5 will be fine at almost like 450 meters per second. So those are two parameters you want to match. We have already know that matching the Reynolds number is very difficult. Let's see how I may be able to use engineering innovation to match the Reynolds number. So here my hand is bound that my velocity in the wind tunnel, in order to match the Mach number, has to be matching this dimensionless perimeter. In other words, the Mach number actually fixes the velocity of what my wind tunnel will be tested at, not the Reynolds number. And I'm off typically by a factor of 10 in terms of matching the Reynolds number. What can you change? And I'll give you the answer. Velocity is bound by the Mach number. This is how big my wind tunnel is. The model is just enough to fit in the wind tunnel. What can I change in order to achieve a factor of 10 increase in my model wind tunnel testing by altering density and viscosity? Do you understand my question? What can I do to increase the density so that this Reynolds number will go up and decrease my viscosity, so the Reynolds number will also go up. In combination, I will achieve a factor of 10 times in the Reynolds number in my wind tunnel. Yes?
You heat up the fluid.
Heat up the fluid. Are you sure? Think about it and try it one more time. Instead of heating, when you heat it, what happens to the density? It decreases. You want to go the opposite way, right? I just cover the screen. You want to what to the density? You want to increase it. How do you increase density? From ideal gas, how do you increase density? Ideal gas. Decrease temperature and increase pressure. You got it. So that led to a wind tunnel called at NASA Langley. And those of you from Hampton may have seen this before. It's called the National Transonic Facility out at NASA Langley in Hampton. Can you see better now? So how do you increase pressure in the wind tunnel? What would you do? You build a pressure vessel. You make the entire tunnel a high pressure vessel that can withstand 10 times the atmosphere, 140 psi. Right? So we just hope it never blew up, because a lot of people will be hurt. And how do you bring the temperature down? put ice, and it's close. How about you use liquid nitrogen? Cryogenic. Cryogenic. So it's also called cryogenic wind tunnel. And this wind tunnel, it was built almost 30 years ago, and it cost about $150 million. So in today's money, that's a lot of money, right? So what you see here, just to give you a size reference, it's not very visible. Here's an automobile. So this is the size of a car. So this is maybe, 2 times a football field. And all this white color material is insulation. The control room and the test section is in this building right here. So by purging the flow of air before they start the tunnel, and all this takes a good part of half a day to a day. They purge all the air inside the wind tunnel, and then they circulate very cool nitrogen from a liquid tank, and they vaporize to become gaseous nitrogen that's at cryogenic temperature, all right, very cold, and then circulate that through the tunnel until they bring it down to minus 150 degrees centigrade, all right, and then they do the experiment. In addition to that, they pressurize it. All of which is trying to do what? One matching. What is that? The Reynolds number. All right, so we go with the extreme to match the Reynolds number as well as the Mach number to get the kind of data, the aerodynamic data that you can use for an actual airplane in flight at 30,000 feet with a size that is 20 times bigger. Okay? So that's a very expensive experiment. That just gives you an idea of what the pitfall regarding model testing. It's not perfect. It's far from perfect. And that's good news for us because that means we have jobs. All right? Even with that testing, I'm going to show you that it's still not perfect. So here's an example of a model airplane, happened to be a supersonic transport way back 20, 30 years ago in that wind tunnel. The model is mounted on a sting, which is nothing but a strut with instrumentation that measures the force, like lift and drag on the airplane. But here's another pitfall. An airplane flying in air is not having a sting attached to it. So they have some interference effect. That's one problem. Then the tunnel wall, which is never far away enough from the airplane, will have influence. Airplane flying in air had no proximity to a wall, but this has. So some correction is needed to account for the fact that the foe see the bounded wall and doesn't always simulate a free flight. All right, so those are the things that create job for engineers like you. Now, totally unrelated, on this airplane, there are pressure tab on the wing at different location, and all what that is, a cavity cut onto the wing and fuselage so that the tubing that is hooked up to a pressure tab on the wing can be routed to the center body and then onto some pressure readout. What do you think those pressure tabs are reading, which is on the surface of the wing? Let me remind you the pedostatic flow that we looked at way back. You have a center port, there's a pedal pressure where the flow stagnant, and you have 4 periphery located pressure tab on the wall of that probe. What does that read? Pedostatic flow. What does that 4 tiny hole from an inch from the nose of the probe you're just reading? What is the center port read? Stagnation pressure. What does those on the side read? Static pressure. Static pressure is the pressure undisturbed. And this is something, if you work for Boeing or Pratt & Whitney, that's something you need to know. Right? So what is the pressure being read on this tiny hole on the wing surface? Still no clue? It's a static pressure, undisturbed, just like the hole on the pedostatic probe that is not being perturbed by the flow or not disturbing the flow. So by measuring those pressure on the wing, on both the pressure side and suction side, you can also check the lift of this model. And that's how experiment is done. Get a feel for this? Okay, so closer to home, At Virginia Tech, this wind tunnel, when you walk between here and Randolph, you see it. So Whittemore is on the backdrop. This tunnel is certainly nowhere compared to the NASA tunnel. It was donated to us from NASA Langley back in the 60s. And it is still a very useful tunnel. We do a lot of experiment in this. This is the fan that drive the air. This is all air and ambient pressure and temperature, not pressurized, not cryogenic. All right, and we do experiment in this tunnel. If I stand here, I will be about this height. This tells you how big this fan is. And it's a 600 horsepower motor. And from this, all we can match is not the Reynolds number. We can only match the speed. So we will be off by an order of magnitude in the Reynolds number, and we know it. There's nothing we can do unless I go to NASA Langley and try to run an experiment that is a couple of orders of magnitude more expensive. All right? So we do test aerodynamic object in here. Here's an example of the work we did several years ago on studying the aerodynamic and the noise of the landing gear in a 1/4, 25% scale model. So this is the landing gear mounted upside down on the tunnel floor with all the details. Remember I said you want a model to look exactly like your prototype in every piece of detail, even cables and everything. So we did it. We make measurement using acoustic photography, acoustic camera, where you can identify the noise sources, where the noise sources is generated. So on landing, if you ever fly next time during Thanksgiving, when the landing gear is deployed, you can feel it and you can hear it because it creates so much drag. So what we're studying is the aerodynamic of those landing gear, how we can reduce the noise, because when they land in the community where there are a lot of people don't want to hear the noise. All right? And then we make measurement using very sophisticated laser diagnostic. So all those are jobs for mechanical engineer where you graduate, because whether it's automobile industry or even bicycle industry, they need this kind of data to improve their product. Questions?